Not a lot to report on the amplifier build. I mean, there's lots of little things, I guess. The first thing is because I put these two capacitors in series, which you may remember I ordered the wrong voltage because I've got a higher voltage now. But I still wanted to use these anyway, so I had these little boards made up. Because these are in series, even though they're the same brand, same voltage, same everything, they do have tolerance. And so they could be different from one another just slightly, especially in their series resistance, which could cause one of them to load differently than the other. So because of that, what you do is you connect, and there's little calculations you can find online, you connect these resistors across the two terminals of the cap, and they're matched resistances, and they basically balance out whatever difference might exist. So they're balancing resistors. So these are 1.5 mega ohm. That then allows these to not load differently from one another, hopefully be a-okay, and then they're in parallel with that big cap, and now I've got some big capacitance there. I don't know that it was a big deal, but hey, we're going all in on this, so let's do it. Something else then you might see here is on the power board here, this big heat sink. That is on a bridge rectifier. That bridge rectifier takes two 6.3 volt windings, puts them in, those 6.3 volt windings are in series for 12.6 volts AC. It then DC rectifies that to, I don't know, probably something close to 18 volts. I didn't do the math on it. That then comes out through into this DC to DC buck converter, where it's then converted back down to 6.3 volts, but 6.3 volts DC, and that's for noise considerations. My wire here is obviously a little fat. I don't know, I may keep that, we'll have to see. Just as long as I can get a tight winding, I'll be happy. But this bridge rectifier was getting pretty hot because it's pulling 5-6 amps through it, and so there were some people noting that there were failures on these. I think you may, if you remember, if you watch an earlier video, you may see where I had a little heat sink on there. Well, I didn't like it. It wasn't enough heat sink, so now I've got a big heat sink on there. So that change has happened. I mentioned before that I was going to use panel meters. They had to be converted from current to voltage so that they could measure a voltage, so they could estimate a current. If that's not confusing, don't worry, who's on first. So these panel meters are 100 milliamps. They measure current through them. I have a 10 ohm resistor in the cathode, connected to the cathode of the power tube, for each power tube of the push-pull circuit. So there's going to be 4 of these, 2 per amp on each cathode. But what I need to do is measure the voltage across that 10 ohm resistor. That voltage then, because it is a 10 ohm high precision resistor, whatever voltage is across that, divide that by 10, and that's your current through that resistor, V equals IR. But these don't measure voltage, these measure current. They're cheap, super cheap, things you can buy on eBay or AliExpress if you're into AliExpress. So there's little tutorials online for how you convert these from current to voltage, and that's what I did. I followed that online. Some key pieces of information actually missing out of that. If you do want to do this, you can always ask me how you do it, because I had to post the question on one of the DIY forums. The short version is, at least for these deals, if you buy the same cheap ones that I bought on eBay, again, they come from AliExpress, I'm pretty sure that's all the same thing. But what you do is you open up the panel meter, you open up the meter, you cut the resistor. There's a resistor in there, you cut it out. You can just cut one leg on it, leave it dangling, which is what I did in case I ever want to go back. But then you've got to figure out what series resistance goes in line so that it measures properly once connected onto that 10 ohm resistor in the cathode. And so by doing the math and then testing it out, I actually wanted to make sure the math was correct too. It's a 680 ohm resistor that goes in series. So it goes from the positive, essentially, side of that 10 ohm resistor connected to the cathode, through 680 ohms to the positive on the panel meter, and then the negative on the panel meter will connect to ground. And that will then be able to measure current through that 10 ohm cathode resistor. I have started building up the amp boards themselves just a little bit. I haven't made a ton of progress. You can see here I've got the sockets for the tubes already connected, or are already installed, soldered in. I wanted to do this side of the board first, so this side of the board will stick up, or at least parts of it will stick up through the top plate of the amplifier. And very common for tube amps to stick the tubes out through the top. And you can also then see these 3 potentiometers on there. They're for balancing various parts of the circuit: the current, the bias current through the cathodes, or bias currents through the tube amps, and then the balance left to right from the input. And then you can actually then see 2 LEDs on the back here. That's the only thing I've installed on the back yet. So as you can see, I got a lot to go. I wanted to do this side of the board first, that way I could flip it over. Well, really, this is the side you're looking at when you're soldering, but clean that off with isopropyl alcohol, which I also did on the power boards. All that flux can leak current. So all of that flux has been cleaned off with isopropyl alcohol on both the power boards and the back side of these. But the 2 LEDs, you can see the LED here on the left. See if I can get in here and point appropriately. This is meant to be an LED based on the circuit, the original circuit. This one is not. This is supposed to have been a resistor, but part of making some of the changes so that this handles the higher voltages so I can run the KT88s. And I think some better, considered maybe better regulation anyway. This part of the circuit gets modified a bit, and this gets a second LED in there. So anyway, I've done that, and the reason why I went ahead and did these LEDs, put those on, is because I've done some matching of LEDs. Because I've got a bit of time, I wanted to make sure that the LEDs were paired up well. There's very little difference between them, but essentially what you do is you take your pile of LEDs, you put use the same resistor for all of them. You just are pulling an LED in and out of the circuit. You measure the current through it, the voltage across it, and you write that down. Then you pull that LED out, you put the next one in, you measure the voltage across it, you measure the current through it, you write that down, and then you find your closest matches. So I had 4 that were they were all very close to each other, but I had 4 that were almost exactly the same. And so those are the 4 that are now installed here, 2 there, and 2 over here. So I'll continue to build these up. I probably should have taken some more measurements on this, because I've got to start thinking about laying out that top plate. Come back to the top plate in a moment. But I did want to show you my test setup here. So this is where I tested my LEDs. Let's remove the box. Well, this actually isn't the LED circuit anymore. I'll mention why that box is there in a second. But I don't have a bench power supply, so a nice adjustable bench power supply would be really cool, but they cost money. And you know what, I had this 12-volt supply ripped out of something years ago, and so I can do enough math and have enough parts sitting around. I can do what I want with a 12-volt supply. So this is what I used. I used the 12-volt supply, a breadboard, some series resistance, and I was able to test my LEDs. I had 10 of them. Again, like I said, I found 4 that matched pretty well. What you can see here, though, this isn't the LED test circuit anymore. This is a circuit for testing bipolar junction transistors. I want matched transistors. Again, I've got the time, so let's do it. Rather than just pulling them out of the package and praying, which is, of course, what they do at the manufacturer. So what I've got here is actually, well, back here is a 5-volt regulator. Again, I don't have an adjustable power supply, so I needed 5 volts, so I bought a 5-volt regulator and set that up. And then here is 2 N5551 transistors. So these are setups to be in a similar circuit. These are 2.49 kilo ohm, 0.1% resistors. And then what's happening is I'm measuring the difference between the base emitter voltage between these two N555-1s. And what's interesting about this is, because I am trying to get matched transistors, you might think that, well, I'm trying to match these two together. That's actually not what's happening. What's happening here is this is the reference transistor. Then you're pulling this one out and replacing it over and over and over again with the pile of transistors under test, device under test, DUT. and you're measuring this delta. And as you can see here, that's what's happening on my meter. And you basically make piles of all the ones that measure similarly on that delta. So what I've done so far is I've not tested very many of them. You can see some are different, right? So this is 3.3 millivolts. These were both in the 1.7 millivolt range. This was a little tighter, 0.6. I have 0 written down here. It's not exactly 0, it's 0.3. And you noticed I had that cardboard box over it. Why? Well, these are supposed to be even susceptible to air currents. So you cover up your circuit, you set and you wait, you let things settle out. Again, you write that down. Then all of the ones that are in the same pile, these are matched. Because, for instance, if these two transistors are both 1.7 millivolt delta VBE, between the reference transistor, the one on the left of that circuit that doesn't get pulled out, then these have to be the same. And I know I've breadboarded this rather than putting it maybe in a printed circuit board where some of the resistances would be the same. But again, you're just looking at that delta. So if that delta is the same, then those have to be the same. So what I'll do is I'll just run through all of these until I've got a pile where they're all the same. I need 4 of the 2N5551s per amplifier. So I'll find the best matching 4 per each one. 2 in one part of the circuit, 2 in another part of the circuit. And then really these should take 6 per amplifier, but because I'm running some higher voltages, I can't run the 2N5551s in every part of the circuit I'm supposed to. So there's a part of the circuit, the ring of 2, they call it. The ring of 2, where in the original design, that's also 2N5551, but for me, because I need the higher capability to handle the higher voltage, this second transistor here in the ring of 2 will be an MJE 340. So here's a 2N5551, here's a 2N551, here's those 2 LEDs I just talked about. So they're matched, the 2N5551s will be matched. I don't think it's probably critical that these 2N5551s are matched, but hey, you know what, I've got the time, I've got the parts, so I'll do it. And then I'll match the MJE 340s, so they'll be nice and all matched up. And for anybody that wants to build this circuit, you can find this on one of the DIY forums, DIY Audio, and so it's a BJT matching circuit. So that's what I'm doing, is testing out transistors. Annoyingly, I will have to change the circuit, and you can kind of see here that they have emitter base, collector, emitter base. Well, you know, a transistor only has 3 pins. Why do I have 5? Ability to plug in 5 pin. It's not because transistors come in 5-pin versions. It's because transistors based on model are different from one another. Really annoying. So the 2N5551, the emitter is pin 1, the base is pin 2, and the collector is pin 3. The MJE 340 is entirely different. The emitter rather is still pin 1, but the base is pin 3 and the collector is pin 2. So you can see the differences between these two. So whenever I go to test the MJE 340s, I'll have to reconfigure my circuit ever so slightly to be able to test it. And again, that's what that circuit schematic showed. So really kind of just trying to do some neat, nice work here on hold. I'm mostly on hold because of European summer vacation. I really need to move to Europe so I can take a nice long summer vacation too. The output transformers that I want to use are coming from Europe, and if I order them now, they come in September. If I order them in later July, they come in September. If I order them in August, they come in September. So they cost a lot of money. They're on hold. I'm on hold. So I can't work on my top plate either because the output transformers will set on the top plate. And just kind of in this holding pattern. So you know what, while I'm in a hold, let's test some transistors. Let's make sure everything is nice. So that's really about it. Yeah. A little bit long for a video about nothing, but you know, so was Seinfeld.